While contemplating the origins of the universe, several profound questions arise. What existed before the Big Bang? If there was no before, what caused the Big Bang itself? For centuries, many believed the answer was simple. An eternal God set everything in motion. Even Isaac Newton adhered to the idea that God created the universe. For a long time, it seemed the universe was eternal and unchanging, with stars being born and dying, planets colliding, and civilizations rising and falling. But on larger cosmic scales and over vast periods of time, the universe appeared almost the same. It wasn't until the 1930s that compelling evidence emerged showing that the universe was expanding, and in the 1960s, scientists discovered the first indications of the Big Bang. This was a revolutionary shift in scientific understanding, comparable to the realization that the Earth orbited the Sun. However, this breakthrough raised two difficult questions. What existed before the Big Bang, and what was space like before it began expanding? Moreover, if everything has a beginning, it follows that the universe must have an end. So, what will cause the universe's eventual demise? British physicist Brian Cox embarked on a quest to answer these questions, and in a groundbreaking revelation, he proposed that the universe may have existed before the Big Bang. Cox stated that the universe likely didn't begin from a hot, dense state, but instead, it could have existed in some form long before the Big Bang. In this view, it's possible to discuss a time before the Big Bang, flipping our conventional understanding of the universe's origins. Brian Cox has transformed science in the 21st century, making complex topics accessible to the public and engaging in discussions that push the boundaries of our knowledge. One of the core ideas he challenged was the traditional view of the Big Bang. Initially, the concept of the Big Bang emerged in the 1920s and 1930s when astronomers observed that distant galaxies were moving away from us, with farther galaxies receding faster. This observation aligned with Einstein's theory of general relativity, which predicted that a static universe would be gravitationally unstable. It either had to expand or contract. The discovery that galaxies were receding taught us that the universe was expanding. This expanding universe doesn't just mean objects are moving apart. It also means that the light from these objects stretches over time, causing the universe to cool as it ages. By extrapolating this back in time, scientists determined that the universe must have been extremely hot in its early stages, a time when even neutral particles couldn't form. The theory predicted that if we looked hard enough, we should detect a faint glow of radiation from the early universe. This became known as the cosmic microwave background, CMB. In 1964, scientists Arno Penzias and Robert Wilson discovered this radiation, providing strong evidence for the Big Bang. From this point, scientists began to extrapolate further, imagining a time when the universe was even hotter and denser, so hot that atomic nuclei couldn't form, and where radiation was so intense that particles would annihilate each other. This era, when particles and antiparticles constantly formed and destroyed each other, led to a completely different view of the Big Bang's origins. But this raised new questions. Was the Big Bang truly the beginning of the universe, or did it have a deeper, more complex origin? Cox argues that the Big Bang was indeed a real event, but it may not have been the start of everything. Instead, the universe may have gone through a period of rapid expansion, known as inflation, before the Big Bang itself occurred. This period of inflation didn't create the universe from a hot, dense state. Rather, it redefined the structure of space and time itself, setting the stage for the Big Bang. The ultimate fate of the universe remains uncertain, but Cox suggests that the Big Bang might not have been the absolute beginning. One possibility Cox explored is that before the Big Bang, the universe existed as an endless, ultra-hot, dense state, possibly governed by quantum mechanics, the physics of the extremely small. The Big Bang would then mark the moment when classical physics took over, driving the expansion of the universe. Another intriguing idea proposed by physicist Stephen Hawking is the no-boundary proposal, where time and space are finite but have no edge or beginning, similar to the Earth's surface, which is finite but without a boundary. Alternatively, Cox suggests that there may have been no universe before the Big Bang at all. Only a vast sea of energy, a primordial soup of sorts. This energy, undisturbed and without structure, could have created the conditions for the universe to begin expanding violently, triggering the Big Bang. This theory challenges traditional religious creation narratives, offering a scientific perspective where the beginning of the universe was not an act of creation, but a natural, albeit extraordinary, event. In summary, while the Big Bang undoubtedly happened, it may not represent the universe's true beginning. What happened before, or whether time itself had a beginning, remains one of the greatest mysteries in cosmology. There was an expanse of energy that rapidly expanded, a process known as cosmic inflation. As this expansion continued, the energy sea transformed into matter through the immense explosion of the Big Bang. The waves of this event left their mark on the universe, creating regions of slightly varying density in the hydrogen and helium gas that formed shortly after the explosion. The denser gas regions eventually collapsed, giving rise to the first stars and galaxies. 9 billion years later, a new star, the Sun, was born, accompanied by 8 planets, including Earth. Nearly 13.8 billion years after everything began, life emerged, and we, humans, gazed up at the light, marveling at the cosmos. Brian Cox isn't alone in discussing the origin of the universe. Recent theoretical physics research suggests a possible window into the early universe, proposing that it could be the latest iteration of a cycle that has been happening for at least once, or perhaps forever. Understanding the early universe requires a blend of general relativity and high-energy particle physics, but the complexity of the math begins to break down when attempting to probe the universe's first moments. This breakdown hints that there's still much we don't know, particularly regarding the singularity at the beginning of the Big Bang. This suggests that the universe was once packed into an infinitely small, infinitely dense point, a concept that challenges our current understanding and indicates the need for new physics. String theory offers a potential solution. It claims that a new model of physics, capable of unifying gravity with the other forces at ultra-high energies, could explain the universe's earliest moments. One of string theory's concepts, the erotic universe, derived from the Greek word for design or fire, suggests that the Big Bang was not the origin but part of a larger ongoing process. This idea has inspired a theory called cyclic cosmology, which posits that the universe repeatedly cycles through big bangs and big crunches, potentially forever, both in the past and the future. Though the cyclic model sounds intriguing, early versions struggled to match observations, particularly the cosmic microwave background, the faint afterglow of the universe from when it was just 380,000 years old. Attempts to tweak the physics of the early universe led to distortions in this light, making the cyclic model less compatible with observations. However, some recent advances in physics have uncovered new possibilities that may restore the cyclic model's viability. These researchers suggest that the universe could be oscillating, expanding and contracting in a grand cosmic rhythm. Some believe this big bounce may have happened only once, while others think it could be a repeating process. Despite challenges, proponents of the cyclic model argue it addresses some of the shortcomings of the Big Bang theory. The Big Bang, as currently understood, is based on a concept called inflation, which suggests that the universe underwent a rapid expansion immediately after the Big Bang. Critics of inflation theory argue it's too neat and might be an oversimplification. Inflation implies a multitude of universes, with our observable universe being just one bubble among many, which raises questions about what exists beyond our universe. On the other hand, the cyclic model avoids this by proposing a recurring universe without needing to introduce a multiverse. This theory suggests that before the Big Bang, there was another universe, one in which entropy increased as time moved backward, potentially reversing the flow of time. This anti-universe idea could explain phenomena like dark matter through a special particle called a neutrino, unique to its own universe. Expanding this concept, we might imagine a mirror universe where time runs backward, yet all physical laws mirror our own. This could account for dark matter and the universe's expansion without invoking inflationary periods. These radical ideas challenge established views of cosmology, suggesting there is still much to learn and discover about the nature of our universe. The concept of a mirror universe suggests that such a universe could have existed before the Big Bang, possibly even before the start of our observable universe. Researchers have proposed some testable predictions for this model, including the idea that neutrinos should exhibit strange behaviors, such as being their own antiparticles or being massless. The absence of primordial gravitational waves, if confirmed by experiments, could further support this model. Understanding the origins of the universe pushes the boundaries of our knowledge, and while we've uncovered a detailed cosmic history, many gaps remain, particularly concerning dark matter and dark energy. The true nature of the universe's beginning continues to elude us, leaving the question of its origin open for exploration. The recent event involving Betelgeuse, a red supergiant star, involved the release of a mass approximately 400 billion times greater than what is typically seen during similar occurrences on other stars or coronal mass ejections, CMEs. This massive expulsion amounted to roughly the mass of the Moon being ejected at an astonishing rate. Astronomers noted that such a significant release from a star's surface had never been observed before. The event was carefully studied, with the Hubble Space Telescope providing real-time data on the surface details, offering an unprecedented view into the aging and evolution of a dying star. This occurrence had a profound impact on Betelgeuse, causing it to lose a considerable amount of mass in a single event. It highlighted how a dying star can undergo significant mass loss far beyond its typical yearly decrease due to solar winds. Researchers believe that Betelgeuse may have violently shed its outer layers and is now in the process of recovering from the aftermath of this dramatic event. Following this darkening episode, the star's behavior changed. Previously, Betelgeuse would vary in brightness at regular intervals. However, after the event, it began to pulse at consistent intervals. Betelgeuse is classified as a semi-regular variable star, meaning it undergoes fluctuations in brightness due to changes in its size and temperature. The star is known to have two distinct pulsation periods, a primary period of about 400 days, likely linked to pulsations in its first mode, and a secondary period of around 5.6 years, though the origin of this longer cycle remains unclear. In their research, scientists employed computational models to gain a deeper understanding of the event. They suggested that a particularly hot gas bubble, resembling an enormous and intense balloon, rose from within the star. These eruptions of hot gas bubbles are sometimes triggered by the star's turbulent and convective outer layers, akin to a pot of boiling soup where material is constantly moving and mixing. When this hot bubble reached the star's surface, it caused a significant release of stellar material and disturbed the star's regular pulsation pattern. The surface of the star began to expand while its deeper layers contracted, shifting the pulsation cycle from its usual 400-day pattern to a new 200-day cycle. Astronomers predict that Betelgeuse's pulsation patterns will gradually stabilize, returning to its normal long-term cycle over the next 5 to 10 years. Regarding the possibility of a supernova, scientists estimate that it could occur any time within the next 10,000 to 100,000 years, based on factors such as the star's color, brightness, size, and age. It is believed that Betelgeuse is in the early stages of helium fusion into carbon, a process that will continue with oxygen, silicon, and eventually iron, before the star's core collapses under its own gravitational pull, resulting in a massive explosion. Since Betelgeuse is located 650 light-years away, any supernova event would take 650 years to reach Earth, meaning we would only be able to observe it after that time. Therefore, it is highly unlikely that we will witness the star's dramatic end within our lifetimes. What makes Betelgeuse unique is that its surface is visible, unlike most other stars, offering a rare opportunity to study how massive stars behave as they age, including these types of dramatic mass loss events. Recently, astronomers made another intriguing discovery: a star consuming its own planet, located 12,000 light-years away in the constellation of Aa Betelgeuse, with its captivating name and prominent position in the night sky, has long fascinated the human imagination. Its significance extends beyond scientific knowledge, having influenced popular culture and folklore worldwide. Betelgeuse's name, derived from Arabic, is often interpreted as the armpit of the giant, and some scientists suggest this origin may reflect the star's association with certain myths and traditions.